Hi, I can't be sure when you're watching this, but I'm recording it in the afternoon. So good afternoon and welcome to my talk. My name is Corey Austin and I'm a postdoc at NASA's Goddard Space Flight Center. I'm speaking today on behalf of the LISA telescope team at NASA's Goddard Space Flight Center. And I'd like to begin by giving special thanks to the folks that developed the Monte Carlo framework that I'm going to be speaking about today. And these folks are Terra, Hardwick, Henock, Legesse, and Joe Howard. As I mentioned, they developed this Monte Carlo framework, and I'm just the person who's been fortunate enough to use it. And I'll be presenting some of the results of that today, but I wanted to be sure to give those folks the proper credit. So we'll jump right into things. NASA is working with a development partner to build 3 prototype telescopes. This will include 2 engineering development units that will include fully polished mirrors, and this is going to let us take a look at the optical performance of the fully assembled telescopes. And then there's also going to be 1 structural thermal model that we can use to evaluate, that we can use in things like vibrational testing. NASA and L3Harris both created Monte Carlo frameworks that we can use for evaluating the manufacturing and build process of the telescopes. This Monte Carlo framework is developed inside of commercial software. In this case, it's Code 5. And what it allows us to do is go through the process of assembling telescopes. And at each step of the assembly process, we can add in the errors and the uncertainties that we expect to take place at each stage. And then we can align or optimize the telescope based on those perturbations. And we can evaluate the telescope's performance at the end of each step and then at the end of the total build process. And we repeat that process 10 or 100 or 1,000 times to give us a sort of a statistical analysis of what it would look like to build a telescope with the parameters that we've laid out. So the perturbations sort of fall into 3 categories, and those are measurement uncertainties, which have to do with only our ability to measure things like the radius of curvature of mirrors or the position of mirrors within the telescope system. The next 2 things, the sorts of perturbations, are manufacturing tolerances, which are our ability to build mirrors to the prescription that we've given, and then the ability to align them to place them within the telescope. The performance metrics, we chose a number of them. We can't look at everything, but we chose a few that we think will be fairly representative of overall telescope performance, and those include wavefront error, bore sight, tilt to length coupling, and then the large pupil position and diameter. So the Monte Carlo framework, as I mentioned, is performed using Code 5, and then we've developed a set of macros that approximate the different steps of the telescope build process. And so each macro corresponds to a different step, and I've got an example of the first part where we add sort of surface figure perturbations to all of the mirrors. And the steps generally have 1 or 2 steps, and they can have 1 or both. And the 2 sorts of steps you can have are adding perturbations and then optimizing or aligning the telescope. And so, as I mentioned before, we will perturb for example, the alignment of the telescope, and then we'll measure all of the parameters to see how that perturbation changed things. And when it's appropriate, when we're simulating, say, the step where we're going to align the secondary mirror to the primary mirror, we allow Code 5 to run its internal optimization and move the secondary mirror as it would in the actual build process. So we do our best in the macros that we wrote in Code 5 that represent each step of the build process to only change the things that we would actually be changing in that stage of assembling the telescope. So as I mentioned, we go through all the steps of assembling a telescope. We measure the performance at each step. We store that data. We store the data at the end, and then we repeat that a number of times to generate some statistics for the telescope. So at this point, we began by evaluating only the measurement uncertainty. And so that gives you a good idea, basically, that the telescope is feasible, but it also more gives you an idea that your Monte Carlo process is working. And so we started with this, and L3 Harris also started with this, and then we compared the results, and we found that we had good agreement between what we had come up with and what they came up with. So we felt like that was a good place to start with things. The next step after making sure that things ran and we had good agreement with only the measurement uncertainties was to begin adding in the tolerances for manufacturing and alignment. And I have a couple of slides where we'll highlight some of those results. So the first one we're going to talk about is the M2 radius of curvature. So the secondary mirror radius of curvature we found was a primary driver for the large pupil diameter. And the current requirement, the current telescope requirement for large pupil diameter is 300 millimeters plus or minus 1 millimeter. So what we did is we evaluated a range of values for the M2 radius of curvature tolerance to find a value that would keep the large pupil diameter within its plus or minus 1 millimeter spec. So you can see nominal is about 25.8 minus 25.8 millimeters, and then the range we went from basically an order of magnitude with a stop in the middle there. And the next slide will show sort of a plot of the results that we found. And so you can see with the sort of loosest tolerance on the left here, we fall out of spec about 75% of the time. When you change that by a factor of 10, all of your builds are now within that plus or minus 1 millimeter specification. And then somewhere in the middle, like a factor of 5, you're pretty good, but you still have a few going out. So just playing with this a little bit, we ran it a few times and sort of just extrapolated that, you know, if you set the tolerance at around 0.067 millimeters, then you should be within. So this is just an example where we set the tolerance to plus or minus 0.065 millimeters. And this is not something that we'll use right away to define what this radius of curvature tolerance needs to be. It's only one part of the equation. The other part of the equation is to look at the performance allocation for large pupil diameter. Is plus or minus 1 millimeter a reasonable number? Do we need to go up from that or down from that? So this is really just an exercise to see how moving that radius of curvature tolerance around affects the large pupil diameter. Another example that we have came from the M3 freeform coefficients. So M3 is a freeform optic whose surface is defined by an XY polynomial. The idea behind this is that the shape of the mirror minimizes pupil wonder and thus the tilt-to-length coupling that comes along with that. Currently, the requirement for that is to remain at less than 0.6 picometers per nanoradian. And so what we did is we, you know, the mirror is spec'd with a set of 4 or more polynomial coefficients. And so we looked at a couple of different sets of these coefficients to see how that would affect the tilt to length coupling. And so you see here in the chart that we have, we looked at 2 different sets of tolerances. The tolerance set 1 is a tighter set, and then tolerance set 2 is a bit looser. And in the case of M3, we have received some as-built data from our development partner, and what we see is that they were able to actually build mirrors that mostly met the tighter spec, which was nice to know. But as we look at the comparison here, even the looser set is only out of spec on about 8% of the builds, but the tighter spec, we are always within the spec there, and it looks like, according to the as-built data that we've received, that this tighter spec is a feasible thing. So those are just highlights of some of the results and some of the ways that we're using the tool. In conclusion, we've developed a Monte Carlo tool for simulating the telescope build process. We validated it against our partner L3 Harris's tool, and then we've used it to evaluate the current set of tolerances. The next steps are to incorporate some more as-built mirror data. We're just starting to get that data in, and so over the next month or so, we'll start incorporating that as-built mirror data, and then we'll be working with simulating, you know, actual mirror data, but looking at how small perturbations to the alignment of those mirrors changes things. And on down the road, once we have some fully assembled telescopes, you know, we'll sort of compare the results that we've received there. That's all I have today. I appreciate you taking the time to listen to my talk, and I hope you have a nice day.